Hello everyone. In this video we're going to discuss how we can compare the probability of error of three modulation schemes: the quadrature amplitude modulation, the phase shift keying, and the frequency shift keying. In addition, we're going to discuss how we can compare the average energy of these three schemes together, right? So in the question we're required to compare the 64 QAM to that of the 8 PSK and the 8 FSK, okay? And we want to do this with respect to two metrics. The first one is the average energy per n node, which is the signal to noise ratio, and the second one is the symbol error probability. And in the first part, since we want to compare the signal to noise ratio, we have to fix the probability of error. So we want to compare the signal to noise ratio with a fixed probability of error for the three schemes. And this graphically has this nice property, this nice, wonderful understanding from a graphical perspective. What is it? Which is that if I have the curve of the three schemes of the probability of error versus the signal to noise ratio, comparing their average energy or the average signal to noise ratio at a fixed error probability means that I want to fix their probability to 10 power negative 3, let's say, and then I want to compare the three average signal to noise ratios. So that's basically what I want to calculate. Okay? So I need to know first what the equation for each curve is. So the equation is given by these three equations. That's the probability of symbol error for the QAM, the M QAM. And remember that this is the symbol error, not the bit error. If you want to calculate the bit error, then you have to divide this probability of symbol error by log 2 to the base log m to the base 2. Okay? And this gives you the approximate bit error probability. Okay? The symbol error probability is given as a function of the Eavg function, complementary error function, or you can multiply outside by 2, giving a 4, and multiply inside by 2, so the 2 here is removed, and you end up having the Markov Q function instead of using the Eavg function. So you can use either this formula or that formula. The same goes for the M PSK as well as the M FSK. Okay? So the question that we want to ask is, what is the value of the signal to noise ratio given that the probability of error is 10 power negative 3? Of course, as you might expect, I need to do some manipulations since I do not have the energy average as a function of the probability of error. I have it the other way around. I have the probability of error as a function of the energy average per n node. So that's basically what I'm going to do here. Okay? So I'm going to write down the equation of the probability of error and equate it to 10 power negative 3. And use the inverse Eavg function. Okay? So I'm going to multiply by 4 over 7. So put this on the other side. And do the inverse Eavg function, which is basically the inverse function of the complementary error function. How do I calculate this? If you do this calculation, you end up having 2.44, roughly speaking. How did I do this calculation? You can use MATLAB, using this command, Eavg inverse of 4 over 7 multiplied by 10 power negative 3, or you can use Wolfram alpha, and in that case, Wolfram alpha gives you the inverse of the error function, not the inverse of the complementary error function. So in that case, I need to subtract this number from 1. Okay? So here 4, 10 power negative 3 over 7. Okay? And this gives you the 2.44. Do some manipulations, you end up having energy average per n node is equal to 249, which is roughly speaking 24 dBs. Okay? Of course, that's a very large number, and the reason is because we want to have a very small error probability. Okay? For the case of the 8 PSK, you do the same trick and do you use the other formula for the M PSK, and you do the Eavg inverse calculation. You end up having the signal to noise ratio has to be 36, which is equal to, of course, this is unitless, and this is equal to 15.7 dBs. Of course, as you can see, there's a difference of around 8 dBs, and the reason is because this 8 PSK is not, we do not have to increase the SNR that high and in order to achieve the same error rate. And this comes at the expense of the rate. 8 PSK means that we have 3 bits transmitted for each symbol, but the 64 QAM means that we have 6 bits transmitted for each symbol, which is twice the rate. 8 FSK has an even smaller error rate, which in that case has an even smaller SNR, which in that case it's 13.16, which is equal to 11 dBs, roughly speaking. Remember that here I've used an equal sign. Why? Because we do not have a direct calculation, an exact formula for the probability of symbol error for the 8 FSK. So we just do an approximation and assume that this is an equality. Of course, if you simulate this system using 11 dBs of SNR, you do not expect to have 10 power negative 3, but you expect to have an even better probability of error. So let's say 10 power negative 4 or so. Okay? And this is basically how we do the calculation of the SNR given a fixed probability of error. Okay? So what if it were to be the other way around? I want to calculate the probability of error given an SNR, a fixed SNR. In that case, the SNR is given in linear. If it was given as 20 dBs, then I need to calculate 10 power the amount in dBs over 10 gives us the linear scale. Okay? So here, 100 linear scale is equal to 20 dBs. Okay, so what do? I just do a direct substitution in the equation. Okay, and thus I end up having probability of symbol error for the 64 QAM is around 5%. The probability of error for the 8 PSK is around 66.2 times 10 power negative 8 times 10 power negative 8 symbols for every symbol. So that's a very small number compared to the 64 QAM, and that's of course as well as at the expense of the rate. The rate here is half the rate here, and the 8 FSK is even much smaller than that. Okay, and remember that this is the bound. It is not really the average probability of error. It's not the average probability of symbol error for the 8 FSK at 100 SNR. The actual value for the probability of symbol error is even less than that at 100 SNR. Is even less than this number. Okay, so remember that this QAM formula is used for square constellation size. So this number has to be even. You cannot have 32, for instance. If you want to calculate the 32 QAM, you cannot use this formula. Okay? It was not going to be accurate because 32 is 2 power 5 and 5 is not even. Okay? So what we learned from this is that whenever we want to compare the error probability, we have to fix the average energy. Whenever we want to compare the average energy, we have to fix the error probability. Okay? And these formulas, you know how to use them. And if you want to use the inverse Eavg function or even the Eavg function itself, you can use MATLAB or any tool or the tables or the Wolfram Alpha. Okay? If you have any questions, please let me know. And if you found this video useful, make sure to share it. Probably most likely other people need it as well.